Despite his degree in thermodynamics, Frank Borman claims that no one knew the test was going to be hazardous. In his own words,
"I don't believe that any of us recognised that the test conditions for this test were hazardous."
He also told the US Senate,
"None of us were fully aware of the hazard that existed when you combine a pure oxygen atmosphere with the extensive distribution of combustibles and the likely ignition. And so this test was not classified as hazardous."
And yet, in Chapter 9 of his book, Men from Earth, Buzz Aldrin writes,
"The only serious hazard of the pure oxygen environment was fire. As every high school student learns, when a smouldering match is put into a beaker of oxygen, it blazes into a spectacular flame. The Apollo cabin was also an oxygen-rich container, and the spacecraft's many switches, electrical equipment, and over 15 miles of wiring could easily short-circuit, providing a glowing match. But the risk was considered acceptable, because in space, the astronauts could instantly depressurize their cabin, while maintaining their own suit oxygen supply."
This statement is in direct contradiction to that of Frank Borman's, who claims that no one at NASA was aware of the fire risk. They either didn't know the risk, as Frank Borman states, or they knew the risk and considered it acceptable, as Buzz Aldrin states. Which is it?
When you got pressurized oxygen, what you have is the same way they find out how many calories is in wet fruit and wet broccoli. A calorimeter bomb, that's what they had there. You know how they fire a calorimeter bomb? Spark plug. Poof! Boosh! It all burns at once. They make sure they have enough oxygen in there to burn everything. That's how they know how many calories come out of it.
Mm-hmm. Yeah.
And that's what they made, a calorimeter bomb. And you can't tell me that he didn't know the dangers of pressurized oxygen, because he's a thermodynamic expert. Welders know it, doctors know it, patients in the hospital know it. But they didn't know it. Oh my goodness, we didn't know that.
Further, as Ralph Renee was able to establish, releasing the cabin atmosphere would not be that simple. According to the Apollo 11 transcript, the depressurization of the lunar module began at 108 hours, 22 minutes, and 6 seconds into the flight.
Tranquility Base, this is Houston. You are go for cabin depressurization. Go for cabin depressurization. Go.
More than half an hour later, Neil Armstrong reported that the cabin pressure was going towards zero.
Pressure going towards zero.
Ironically, as Buzz Aldrin stated himself after depressurization,
Sure takes a long time to get all the way down, doesn't it?
even if they could depressurize the spacecraft in time, there is still another problem. The Apollo spacecraft was designed for astronauts to work in shirt sleeves. They would only need to wear the spacesuits during liftoff and during depressurization of the cabin. Suppose a fire broke out while the astronauts were in shirt sleeves. Putting on a spacesuit can take a long time. North American Aviation's Frank Hendel wrote about this in his article.
The best way to extinguish such a fire is by a rapid decompression to 0.2 psia or less, but donning of a pressure suit takes approximately 5 minutes.
Of course, oxygen at 5 psi doesn't burn as rapidly as oxygen at 16 psi or 20 psi, but 5 minutes would certainly cost the astronauts valuable time. And even the 5 minutes it takes to put on the spacesuit is in doubt. The old Mercury, Gemini and Apollo suits were one-piece garments, through which astronauts would enter through an external zipper. The modern space shuttle suits are two-piece garments, which astronauts would don by sliding in and screwing together. These modern spacesuits take considerably longer than 5 minutes to put on, so long that NASA has been forced to find quicker ways of suiting up for spacewalks.
And then we literally just open this hatch, and then we open the back hatch of the suit that has the backpack on it.
That's actually, the second door is actually part of the suit.
It's part of the suit, and then you literally step into the suit.
And take off collecting samples of the moon's surface. Mike says he can get into these spacesuits and be on the moon's surface in less than 10 minutes. Up till now, getting in a spacesuit has taken hours.
What good is the plan to depressurize the cabin if it'll take hours just to put the suit on, and another half an hour to depressurize the vessel? Remember too, these suits weren't fireproof. As we later learned, the Apollo 1 suits were breached by the fire. And as stated previously, at 5 psi pure oxygen, even various fireproof materials like asbestos will burn. In other words, it doesn't matter whether you have 16 psi, or 5 psi, or 20 psi. If you trigger a fire in pure oxygen, it is a fair bet you are about to become toast. It's also worth noting that the Apollo 1 mission was to be flown using a Block 1 type CSM. The Block 1s were for Earth orbit flight, and the Block 2s were for circumlunar flights. As David Shaler writes on page 436 of his book, Disasters and Accidents in Manned Spaceflight, the escape of the crew had been foiled by the design of the plug-type spacecraft door, designed to seal it firmly and to be opened from the outside, and no EVA was planned on the Block 1 spacecraft, so there was no need to open the door in orbit. This means that if a fire broke out, the astronauts wouldn't have been able to depressurize their capsule by the quicker and easier method of blowing the hatch open. So clearly, the justification for the use of a hazardous atmosphere is false. It is also false that the fire risk was the only danger posed by pure oxygen. As we established previously, another danger posed by pure oxygen is actually breathing it. As David Baker states on page 39 of his book, The History of Manned Spaceflight,
on Earth, atmosphere consists of a 760 mmHg mixture of 21% oxygen and 79% nitrogen, plus several trace gases that can be ignored for temporary and artificial environments. Because the quantity of oxygen in the lungs regulates the amount entering the blood, any appreciable increase in partial oxygen pressure of 160 mmHg will cause irritation of mucous membranes and could disturb the function of critical enzymes. However, even a moderate fall below the normal partial pressure value quickly causes brain damages and severe side effects. The option available to Mercury engineers were that the capsule could contain either a two-gas mixture of oxygen and nitrogen at sea level pressure, 760 mmHg, or a single-gas atmosphere of pure oxygen at about 160 mmHg. Tests revealed that the pure oxygen pressure limits were between 150 mmHg and 345 mmHg. Oxygen pressure for a single-gas atmosphere outside these limits would cause severe, if not permanent, damage.
the pressures Baker speaks of correspond to 2.9 psi and 6.67 psi. In his book, when talking about a 16.7 cabin atmosphere, Buzz Aldrin states,
For several years, NASA and North American aviation managers have been actively debating the pros and cons of this cabin atmosphere. Early in the program, medical experts had feared that breathing pure oxygen for prolonged periods would be harmful to the astronauts. But the long-duration Gemini missions had disproved this. Astronauts could work for weeks in space, breathing pure oxygen at low pressure.
What Aldrin fails to mention is that those Gemini missions were flown with a cabin pressure of 3 psi, which is within the safe pressure limits for breathing pure oxygen. Not only did NASA put the Apollo 1 crew in an atmosphere they knew was flammable, they also put them in an atmosphere that could have suffocated them, a danger that had been known since the Mercury project. Also note Aldrin's admission that NASA and North American Aviation had for years debated the use of a pure oxygen atmosphere greater than sea level pressure. This is in direct contradiction to what Harrison Storms would have you believe, that North American Aviation wrongly assumed NASA was doing the test at 5 psi.